Hello, this is pure bending example number 2. The problem reads, a metal strap with a rectangular cross-section is bent around a solid cylinder of radius 20 inches. Given that the height of the strap is 0.05 inches, calculate the maximum stress in the strap as it passes over the cylinder. Modulus of elasticity is 29,000 KSI, which is, of course, that of steel. That's annoying. So this would be a problem where maybe there's some type of an industrial thing where strapping or metal straps are being fed through a machine, and if they feed them around a spindle that's too small in radius, then it might cause the material to yield, and it might compromise the integrity of whatever it is that they're making. So we need, in this case, to make sure that the radius is large enough that the metal doesn't yield as it's passing through there. So that's basically the premise of this particular problem. Okay, so here's the strapping in the picture, and I'm going to work this problem out in OneNote. So one of the things that I'll do is I'll go first to our equation sheet and reference the equations that we'll be using, and you can see that those are given here, my over I and E times y divided by rho. And it's that second equation that we'll find most valuable at this point. So we'll take sigma is equal to a minus E times y divided by rho. All right, so let me shut that off. Okay. So in this equation, rho is the radius of curvature, and it's measured from the center of curvature to the neutral axis or the neutral section of the whatever the element is that's being bent. So in this case, let's go ahead and define some coordinate systems. So I'll take y as being upwards like that, and I'll take this as being the z-axis. So that means that the stress that we're going to be calculating is sigma in the z direction. Now what I'm going to do is I'm going to look at a section over here as the strap is being passed around that spindle. So I'll call that section AA like that. And then I'll draw that cross section down here so we have a better idea exactly of what it is that is being bent. So now in this view, this would be the y-axis. This would be the, let's see, yeah, this would be the x-axis. And then the z-axis would be coming out of the plane of the screen at you. And this would, of course, be section AA. So the top of that is being pushed into compression, so it's inducing a moment that is positive. Now the radius of curvature rho is different than the radius of the cylinder r. So if we look at a drawing that has the strapping drawn a little bit thicker, then you can see the difference here between the radius of the cylinder r and the radius of curvature of the strapping rho. So there is a finite difference there. It's not terribly large in terms of actual numbers, but it is large enough that it makes a small difference in our calculations. So we can say that rho, the radius of curvature of the strapping, is equal to r, the radius of the cylinder that the strapping is being wrapped around, plus half of the height. And I should be complete and go back down over here and say that this is the height h, and it's given as a rectangular cross section, so that means that the centroid is at the mid height, or the centroid is at the axes of symmetry of the cross section. So back over here, we could say that this is equal to r, which is equal to 20 inches plus half of the height. The height of the strap is 0.05 inches. So that means that our radius of curvature is 20.025 inches. So given this, then all we need is y. And if we're looking for the maximum value of the stress, then what we'll do is we'll go in here and we'll put in y at the top fiber or at the bottom fiber. So down here, y would be equal to minus h over 2. And then up here, y would be equal to a positive h over 2. So we can calculate those stresses, and I'll do it like this. I'll say minus E, so this is 29,000, KSI. And then I'll go ahead and put in plus or minus H over 2. So that is 0.05 inches divided by 2. And then in the denominator, I'll put in our radius of curvature, 20.025 inches. And then what that gives us is a stress that is either equal to minus or plus 36.20 KSI. So if we're looking at the top fiber, then Y is positive, so that gives us a negative stress, a compressive stress. And if we're looking at the bottom fiber, then Y is negative, so then that gives us a positive stress or a tensive stress. So what I'll do lastly is I'll sketch the distribution of stress on that cross section. So I'm looking at the side view of this, so plotting the side view like up here. And if I do that, then let's see, 1, 2, 3, 4, 5, 6 squares. Then here's a section break, here's a section break. So this is the height H, and the neutral axis is at mid height because it's a rectangular cross section. And then what I can do is I can plot the stress sigma, and it's sigma sub z. So we go out here, I'll take a scale of say 10 KSI per square. So 10, 20, 30, 36 KSI right about there. And then same thing down here. And then if I take just a second and use my straight edge to maybe make it a little bit better or less worse, then we can get the stresses in here. Like that. So they're acting in compression above the neutral axis. They're acting in tension below the neutral axis. So it's like that. So 36.20 KSI compression, and then down here 36.20 KSI acting in tension. So and just to be complete, then this is the z-axis and that would be the y-axis. So if the material being bent was actually steel, most steel has a yield stress above 36 KSI or at least 36 KSI, so this would probably be sufficient. If you wanted to be certain, then make that drum a little bit larger, say 24 inches instead of 20 inches. Okay, and if we look at the distribution of stress drawn just a little bit more neatly, then that's what that looks like. So hope that this helps.